Hello, my name is Dr. L'Hopital. We have a triple integral where E is the solid that lies within the cylinder, x squared plus y squared equals 4, above the plane C equals 0, and below the cone C squared equals 16x squared plus 16y squared. Here is our sketch, where we have our cylinder in the origin, and we have our cone above the plane C equals 0. Basically, it's like having a cone inside of a cup. If we cut that cup in half, we would see this area, which is the area that we want. So we know that x squared plus y squared equals r squared. And our cylinder is x squared plus y squared equals 4. Therefore, r squared equals 4, so our radius equals 2. We also know that c squared equals 16x squared plus 16y squared. We factor out the 16, we end up with x squared plus y squared, which we know it's r squared. So we replace it, and we end up with c squared equals 16r squared, which gives us c equals 4r. This is our limit for c from 0 to 4r. And our limit from r is from 0 to 2. And we know that for theta, our limit is from 0 to 2 pi, because it is a circle in the x-axis.
Thank you. Hello, my name is Senor Mr. Dr. Jacobian. Okay, now we have our integral. It is a triple integral of x squared, where in this case we need to turn this from rectangular into cylindrical. So we use this formula right here, which is x equals r cosine theta. Plugging in for our x, we see that we end up getting r squared cosine squared theta, and our dv is r dz dr d theta. Okay, now for our bounds. Our bounds, since we have a constant with variables, we integrate that first, and then our constants on the outside. Okay, now we can integrate. Here we have our integral reduced, which is r cubed cosine squared theta dz dr d theta. Integrating, we see that once we integrate with respect to z, it's just a plain z multiplied to it. So once we evaluate from 0 to 4r, we get 4r to the 4th cosine squared theta dr d theta. Here, when we integrate with respect to r, we end up getting 4r to the 5th divided by 5 cosine squared theta d theta. That will bring us up here. Once we get that, we can factor out our 4/5, and that will leave us with this integral.
Hello, I am Dr. Lagrange, and evaluating r from 0 to 2 is 2 to the 5th is 32. Pulling that out times a 4, we are left with 128 over 5. After evaluating for r, we are left with the simple integral of cosine squared theta d theta. Now we remember back from 3rd grade that a identity for the cosine squared would be the double angle identity, which is 1 plus cosine 2 theta all over 2. Factoring out the half multiplied to 128 over 5, we are left with 128 over 10. And we now have the integral of 1 plus cosine 2 theta d theta. Once we integrate with respect to theta, we are left with theta plus sine of 2 theta over 2, evaluated from 0 to 2 pi. Plugging in a 2 pi in theta, we are left with 2 theta plus sine of 4 theta over 2, which is 0, minus the zeros. Now we have 2 pi times 128 over 10, which simplifies to 128 pi over 5, and that is our final answer.